Welcome to 4 Dharma Turn, where we explore the profound science of the mind and uncover how you can reshape your brain and life through the power of neuroplasticity. Neuroplasticity, or neuroplasticity, refers to the brain's remarkable ability to reorganize throughout life in response to experiences, learning, injury, or environmental changes. This brain's flexibility challenges the traditional view that the brain is a static organ after maturity, revealing it as a dynamic system capable of continually adapting and evolving. Discoveries in neuroscience over the past few decades have shown that neuroplasticity is not just a phenomenon during childhood development, but continues throughout life, even into old age. This understanding has revolutionized the approach to treatments for various neurological conditions and opened up new possibilities for personal growth and self-transformation, enabling interventions based on brain reconfiguration in areas such as post-stroke rehabilitation, mood disorders, and even cognitive enhancement in healthy individuals. Neuroplasticity is based on neurons, the specialized nervous system cells that transmit information through electrical and chemical signals. These signals are transmitted through synapses, the junctions between neurons, which play a crucial role in neural communication. Each neuron can form thousands of synapses, creating an intricate neural network underlies all cognitive, emotional, and motor functions. Synaptic plasticity, which involves the ability of synapses to strengthen, synaptogenesis, or weaken, synaptic pruning, in response to activity, is central to understanding how the brain adapts and changes. Studies in animal models have shown that synaptic plasticity is mediated by complex molecular processes, including the modulation of neurotransmitter receptors, such as NMDA and AMPA receptors, essential for long-term potentiation, LTP, and long-term depression, LTD. In addition, myelination, the process of covering nerve fibers with myelin, plays a crucial role in plasticity by increasing the speed of transmission of nerve impulses. Research has shown that myelination is susceptible to environmental experiences and learning, suggesting that neuroplasticity occurs at synapses and in the supporting structures surrounding neurons. This expanded understanding of plasticity now includes remodeling the extracellular matrix, the influence of glial cells, and the formation of new blood vessels in the brain, demonstrating the interconnectivity and complexity of the neuroplasticity mechanisms. The concept of activity-dependent neuroplasticity reveals that experience dynamically shapes the brain. Repetition of activities, such as learning a new language or practicing meditation, strengthens the neural pathways involved, while lack of use can weaken these pathways. The adage, neurons that fire together, wire together, often describes this principle, which summarizes the idea that repetition strengthens synaptic connections. Long-term potentiation, LTP, manifests this principle, representing a sustained increase in the strength of a synapse in response to repeated stimuli. LTP has been widely studied as one of the primary mechanisms underlying learning and memory, and is dependent on the activation of NMDA receptors that allow the entry of calcium ions, triggering a cascade of molecular events that strengthen the synapse. In contrast, long-term depression, LTD, plays a role in weakening synapses, allowing the brain to remain flexible and adaptable. LTD is mediated by mechanisms distinct from LTP, involving the removal of AMPA receptors from synaptic membranes and destabilizing the synaptic cytoskeleton. This duality between LTP and LTD illustrates how the brain balances the retention of important information and eliminates redundant or obsolete information, which is crucial for cognitive optimization. Furthermore, recent studies suggest that activity-dependent plasticity is not limited to synaptic strengthening and weakening, but also includes changes in the density of dendritic spines and the reorganization of entire neural circuits, allowing for large-scale adaptations in response to environmental demands. Several factors influence the brain's ability to reconfigure itself. Age is one of the most important determinants, with plasticity being most pronounced in childhood due to the high rate of neurogenesis and the formation of new neurons. During this period, the brain is susceptible to environmental influences, allowing for rapid development of cognitive and motor skills. However, recent research indicates that neurogenesis continues into adulthood, especially in the hippocampus, a region critical for learning and memory, suggesting that the potential for neuroplasticity never completely disappears. Studies of adult neurogenesis have identified the role of brain-derived neurotrophic factor, BDNF, and other growth factors in regulating the proliferation and differentiation of neural progenitor cells into new functional neurons. Environment and lifestyle also have a significant impact. An enriched environment with cognitive, social, and physical stimuli promotes brain plasticity. Studies in animal models have shown that rats raised in enriched environments have increased synaptic density, neurogenesis, and greater resilience to stress compared to those in impoverished environments. Practices such as meditation, regular exercise, and a healthy diet have been associated with increased neuroplasticity due to their ability to reduce oxidative stress, improve cerebral vascularization, and promote the release of neurotrophic factors such as BDNF. In addition, sleep plays an essential role in consolidating memories and strengthening synaptic connections during the day. Sleep deprivation can significantly negatively affect plasticity, impairing learning and memory. Functional neuroimaging studies have shown that sleep deprivation leads to decreased functional connectivity in the hippocampus and other regions critical for memory, indicating a direct link between sleep quality and the brain's ability to adapt and reorganize. Neuroplasticity also has profound implications for recovery from brain damage. When an area of the brain is damaged, other regions can be recruited to take over its functions through cortical reorganization. This phenomenon is particularly evident in patients who have suffered a stroke, where plasticity allows partial or total recovery of motor and cognitive functions through intensive and targeted therapies. Cortical reorganization is supported by the formation of new synaptic connections and the migration of progenitor neurons from regions such as the subventricular zone to damaged areas, where they can differentiate and integrate with existing circuits. In addition, the practice of techniques such as motor visualization, where the patient imagines the execution of movements, effectively promotes plasticity in motor regions, even when physical execution is limited. Studies using functional magnetic resonance imaging, fMRI, techniques have demonstrated that motor visualization activates brain areas similar to those involved in the actual execution of movements, suggesting that simple imagination can induce plastic changes in neural networks. This highlights the power of the mind to directly influence brain reorganization, suggesting that recovery of lost functions can be facilitated by intention and mental focus, demonstrating the deep interconnection between body and mind. Furthermore, interventions that combine electrical brain stimulation with motor rehabilitation have been shown to further enhance the effectiveness of neuroplasticity in recovering function after brain injury, offering promising new therapeutic avenues for neurological rehabilitation. Neuroplasticity shapes our abilities and capabilities and plays a crucial role in shaping and reshaping our identity. The experiences we have, the habits we cultivate, and the mental practices we adopt directly influence the architecture of our brains. This ongoing process of reshaping means that identity is fluid and can be transformed through deliberate practice. Neuroimaging studies have shown that contemplative practices, such as meditation, promote structural and functional changes in brain regions associated with emotional self-regulation, empathy, and self-awareness. For example, experienced meditators demonstrate thickening of the prefrontal cortex, the area related to planning, decision-making, and moderating social behaviors. This suggests that regular practice can shape how we think and relate to the world. Furthermore, meditation has been associated with changes in the amygdala, a region involved in emotional processing, with a reduction in amygdala volume correlated with a decrease in emotional reactivity. These brain changes reflect an increased capacity for emotional regulation and a shift in perceptions of self and the world, suggesting that identity can be actively shaped through neuroplasticity. This perspective offers an optimistic view of the human potential for self-transformation, implying that with practice and time, we can rewire our minds to align our actions and thoughts with our highest values and aspirations. Emotions are also profoundly affected by neuroplasticity. Repeating negative emotional patterns, such as rumination or fear, can strengthen neural pathways associated with stress and anxiety, making these emotional states more prevalent. This phenomenon is known as emotional fossilization, where specific emotional patterns become so entrenched that they dominate an individual's emotional response. However, plasticity also allows us to cultivate positive emotions. Mindfulness and compassion techniques effectively rewire neural networks to promote emotional well-being, showing that we can train our brains to respond more healthily to adversity. Studies show that regular mindfulness practice is associated with increased functional connectivity between the prefrontal cortex and the amygdala, suggesting greater cognitive control over emotional reactions. Furthermore, practicing compassion has been linked to increased activation in brain regions involved in empathy, such as the anterior cingulate cortex and the insula, demonstrating that repeated positive mental practices can lead to lasting changes in brain structure and function. This process of emotional rewiring illustrates how neuroplasticity is a tool for improving cognitive abilities and transforming our emotional lives, fostering resilience and a more balanced and positive outlook. The understanding that we can consciously shape our emotions through mental practice provides a powerful argument for adopting mindfulness and compassion practices as tools for self-transformation and emotional well-being. Finally, neuroplasticity is the basis for lifelong learning. Regardless of age, the brain adapts and learns from new experiences. This concept is particularly relevant in today's web-based society, where continual learning is essential for adapting to rapid technological and social changes. And use it or lose it is crucial here. Continued practice and exposure to new challenges are essential to keeping plasticity active and avoiding cognitive decline. Studies have shown that regular practice of cognitively challenging activities, such as learning a new language, playing a musical instrument, or solving complex problems, is associated with increased synaptic density and neurogenesis in regions critical for memory and learning, such as the hippocampus. Furthermore, continued learning, whether through formal education, hobbies, or new skills, can slow cognitive aging and enrich life unexpectedly. For example, studies in the neuroscience of aging have shown that individuals who maintain an active intellectual life tend to have a lower incidence of neurodegenerative diseases, such as Alzheimer's-Ader, and preservation of cognitive functions. By adopting an active and curious attitude, we can maximize our mental and emotional potential, using neuroplasticity as a tool for personal development and achieving lasting well-being. Therefore, neuroplasticity supports lifelong learning and represents the scientific basis for lifelong learning to achieve a rich, complete,